Let me start by thanking the organizers, Rampe, Atsushi, and Ryo, for inviting me to this meeting. I really wish I was there in person. One reason is because I wasn't able to attend most of the talks due to the time difference. But also, it's been a long time I've been to Sendai, and Sendai is one of my favorite places in Japan. And in particular, I miss having gyutan with oxtail soup on the side. But I digress. Let me go back to the talk. The topic of the talk is dark energy from massive gravity. And this topic was indeed quite popular maybe 10 years ago or so. But over the years, it fell out of fashion due to some complications we have building cosmological models in the usual Durham-Gabadazze-Tolley massive gravity. I will talk about this a bit, but today I will try to justify why we should go back to the massive gravity in a new framework, in a new theoretical framework, and in the context of dark energy models. And this is based on work done in collaboration with Michael Kenna Ellison, who was my student at Portsmouth, and he graduated last year, Rampe Kimura from Waseda, and Kazuya Koyama from Portsmouth. Okay, so when I talk about getting dark energy models from modified gravity, probably not many of you immediately think of massive gravity, because that's not the simplest thing you can do in order to get a dark energy model. Arguably, the simplest thing you can do is to add a single degree of freedom, typically a scalar degree of freedom, and then see what's happening. And indeed, with the addition of a scalar, you open up a lot of possibilities. First of all, due to the scalar's dynamics, you can promote the cosmological constant to a fluid with an equation of state that's time dependent. So it's like a dynamical dark energy type behavior at the background level. But also in the scalar perturbations, you get to see a lot of effects, especially in the matter perturbations. And you generate, well, you might generate some anisotropic stress and so on. And also in the tensor perturbations, there will be some contributions in principle to the speed of propagation of the tensor modes. This is not always true, but in some cases, that's one of the possibilities. And the typical theoretical framework that we use is the scalar tensor theory class. And that consists of Horndeski and then the newer additions of beyond Horndeski and Dost type terms. And this gives you a really big theory class. And depending on what you want to do, you can fix your theory by fixing the arbitrary functions in the theory class description. And you can do a lot of different applications for dark energy, starting from some interesting matter descriptions like k-essence to some really contrived scenarios like self-tuning models like FAT4. And on top of that, we also have the effective field theory description, which allows us to interpret data using only a handful of parameters. So it's a good way to also classify different types of terms depending on what type of signatures they lead to. So everything looks really nice in the case of scalar tensor theories, but after the direct observation of gravitational waves, things started to change slightly. And one of the major roles is played by the observation of the binary neutron star merger, which tells us that the tensor modes propagate at the speed of light to a very good accuracy. So that rules out any model that requires a tensor mode that is not propagating luminally. There are also other effects, like you can get these types of interactions with two derivatives of the tensor mode from some beyond Horndeski terms. And these types of terms actually lead to interactions that are quite efficient at LIGO scale. So gravitational waves decay into the scalar field through this interaction term. And this puts bounds on the alpha H parameter in the EFT language. And you can also get terms with one derivative. And these types of terms typically arise from many nonlinear interactions, self-interactions of pi, well, in the closed Lagrangian, that involves at least two covariant derivatives of the scalar. And these types of terms actually lead to an instability in the presence of gravitational waves at LIGO scale. And this puts bounds on the alpha B parameters. But of course, I think Scott is in the audience, so he might object to this. There are some caveats that come along with these. First of all, the cutoff of the effective field theory is worryingly close to the LIGO band. So you might wonder whether it would be reasonable to put bounds on the EFT parameters so close to the cutoff scale where the EFT is known to be invalid. But again, I think we need more information on this to typically decide. But this is definitely something to worry about. And the second is that the last two items that I talked about, the calculations and the predictions of these effects relies on the assumption that scalar perturbations, scalar fields perturbations propagate at subluminal speeds. But if you do not worry about any of these assumptions or maybe problems, then, and you take all of these seriously, the vast theory class reduces to this tiny Lagrangian. And there are only two terms here, two functions here. One of them is just describing fancy matter fields like k-essence and quintessence. And then the C describes, well, tells you that the modified gravity theories you can have are only those that are related to GR via conformal transformation. So this is what's left after all these restrictions are applied. And what does it tell us about dark energy models? Well, the remaining dark energy models then are just simple extensions of lambda CDM. So lambda CDM is there, and it can be obtained when you go to some limit of some limit of the parameters. But what this really means is, if in the future we do not observe any departure from lambda CDM at the background level or at the perturbations level, then you cannot really rule these models out, right? These are not falsifiable models in that sense. And they, the remaining models do not address the naturalness issues associated with the cosmological constant problem. So what do we do? I guess one easy way would be to look for other modified gravity theories and look for alternative models. But then again, scalar tensor theory seems to be quite powerful because many modified gravity theories already have scalar degrees of freedom, sometimes one of them. And maybe I can rewrite this question in a different form. Is the scalar tensor class an accurate proxy for other theories with a scalar mode? So maybe I don't have to do a calculation for some modified gravity models. Maybe scalar tensor theory's conclusions would still apply to more general models. And this question is a difficult question to answer formally. I don't know how to answer it. But the best thing I can do is to come up maybe with some counterexample or an example to scalar tensor theory being valid for other theories. And the natural thing to look at, I think, is to go back to massive gravity. And my goal is twofold. One is to obtain an alternative dark energy model, but also maybe to be able to compare with some of the results you get from scalar tensor theory, especially in the context of gravitational waves, to understand to what extent I can use the scalar tensor theory. And I said naturally my first choice is massive gravity because there are many theories that are similar, that give you similar dark energy models to the ones in scalar tensor theory. You have lots of common properties between the scalar tensor models and massive gravity. Although you have many degrees of freedom in massive gravity, you have only a single scalar degree of freedom. You have a screening mechanism, and you have a similar scale for the EFT cutoff. And the punchline of the talk is that I will show you that you can actually get some potentially falsifiable dark energy models. But I will also argue that the scalar sector in the massive gravity models are not fully described by scalar tensor framework, although qualitatively you have many common features. Okay, so let me start with massive gravity then, after this big introduction about scalar tensor models. So in this slide, I'm basically summarizing the standard massive gravity model, which was introduced in 2011 by Deram Gabadadze and Tolley, or dRGT for short. So this is the action for this theory. The kinetic term for the spin-2 field is given by the Einstein-Hilbert term. So this is like a canonical kinetic term, if you wish. And the masses are provided by these 5 potential functions. And these are constructed by the square root tensor. Here, F is the fiducial metric. This is what you use to define mass terms. So with respect to this fiducial metric, you define the mass terms. And this is nothing but Minkowski pulled back to space-time coordinates. So you have eta AB here, and you have 4 scalar fields. And these scalar fields each correspond to a broken diffeomorphism degree of freedom. So these are basically Stückelberg fields that reinstate the broken diffeomorphism invariance and reinstate the covariance. And these fields enjoy a Poincare symmetry due to the Minkowski metric in the field space. And these En are just elementary symmetric polynomials, and they stop at 4 in 4 dimensions. Okay, that's basically massive gravity in a nutshell. If you try to construct a cosmology in it, then things become interesting. First of all, you don't have flat Friedmann-Lemaitre-Robertson-Walker. It doesn't expand, but you're allowed to have an open universe solution with the negative curvature. So with this metric, the compatible fiducial metric is achieved with this Stückelberg field configuration. And using this in the definition of F mu nu, you find that this is just, well, this is still Minkowski, but written in some funny coordinates that look like some open universe cosmology. So this is Minkowski in open chart. Okay, and with these, you can go back to the action and derive the equations of motion. And for the background evolution, you have these equations of motion. First of all, the effects of the mass term in the equations of motion are provided by these 2 functions L and J, and they are defined here. And they're just polynomials of this psi quantity, and this is defined here. And psi is basically can be interpreted as the ratio of the 2 scale factors. So the scale factor in F metric divided by the scale factor in G metric, or the physical metric. Okay. And the coefficients in these polynomials are just constant in dRGT because alphas, the mass parameters, are constant in dRGT. And then there's a contribution to the Friedmann equation, and there's a contribution to the H dot equation from the mass term. I've also added some matter term because then it becomes easier what these contributions from the mass term correspond to in the fluid language. So J is kind of like rho plus P for the effective fluid, and L is like the energy density. The key point here, however, is this last equation, which is the Stückelberg equation of motion. And you can see there seems to be some branching here, but you can actually forget about the stuff in the parentheses. That cannot be 0, because if that's 0, your physical metric becomes just Minkowski in open chart. So that's not a cosmology solution. The non-trivial cosmological solution is J equals 0. Okay, and there are many ways to see the effect of J becoming 0. One of them is that you can see that when J equals 0, the rho plus P is 0. So it acts like a fluid with an equation of state -1, or a cosmological constant. You can also say that J equals 0 basically has constant roots. That means psi will be constant. So any function of psi will be constant, and the energy density contribution will become a constant. So for dRGT cosmology, the background is indistinguishable from lambda CDM. Okay, but if you want to find a way to discriminate this with respect to lambda CDM, you go to perturbations, look at cosmological perturbations, and you see a surprise. There are 3 more degrees of freedom in massive gravity with respect to GR. There are scalar polarizations of graviton and vector polarizations of graviton, and all 3 of them have kinetic terms that are proportional to this J quantity. So they vanish on shell. And this is the source of the problem. There's an infinite strong coupling, or you can interpret this as nonlinear ghost instability, but the bottom line is you cannot trust perturbative expansion around this background. Okay, so that's the problem with dRGT cosmology. There were several ways proposed to resolve this issue, and I classified them into 3 categories, but I'm not going to go into too much detail. But you can either break isotropy or homogeneity in the background in order to revive or resolve this strong coupling problem, or you can add more degrees of freedom, and with these you can actually ensure that the kinetic terms do not vanish, and there's no limit in adding degrees of freedom, and there has been lots of works on this topic. I'm just citing a few of them, and some of them were relatively successful, and some of them not so much. Or the third option is to break the symmetry of the theory. And this has been mainly done by breaking Lorentz invariance, either by providing a preferred foliation or some other constraints that gets rid of the Lorentz invariance. And the approach I'm going to take in this talk is going to be the third approach, the breaking the symmetry of the theory, but I will do it in a slightly different way than that's been done here, in a way that preserves Lorentz invariance and preserves the number of degrees of freedom in dRGT. So let's talk about this a bit. The symmetry I'm going to break is the global translation symmetry in the field space. So if you remember, the field space enjoyed a Poincare symmetry. So I'm just going to get rid of the translation symmetries. And applying this to the massive gravity context was first proposed in this paper by Deram and collaborators. And the advantage of this, that breaking this global symmetry does not introduce any new degrees of freedom. And then we expect that the theory space to be continuous with dRGT. But what it gives us as an advantage is that now we are allowed to add terms that depend on phi without any derivatives. Okay, so you can build this new invariant, which is basically the norm of the scalars, as a new building block and construct terms out of this. And then you can go ahead and define all the possible invariants you can write, and then do some constraint algebra, or look for ways to remove unwanted degrees of freedom via some degeneracies and so on. And you can find the complete class of theories. And a simpler way, a shortcut, which can be also applied, is to start from dRGT and then transform the physical metric by a conformal transformation and the internal metric by a series of disformal transformations. And both of these ways actually give you the same result at the end of the day. And this is what we have done in this paper with Kimura-san. And we found in this paper 2 classes of massive gravity. I'm going to be focusing on one of them, the one that actually contains dRGT in some limit. And it's given by this action. So this is, again, a theory class for massive gravity theories with broken shift symmetry in the field space. And there are 6 arbitrary functions that depend on the new invariant x. So you have a non-minimal coupling and also a counter term for that. Then you have some mass terms which look like dRGT but generalize it. First of all, the mass parameters alphas that were constant in dRGT are now functions of this new invariant. Also, this fiducial metric now gets a deformation term, a disformal deformation given by this D function. Okay, and this is again a class of theories. Depending on what you choose for the functions, you can specify what theory you are in. Some examples would be, of course, as I mentioned a few times, dRGT can be obtained if you turn off the non-minimal coupling, turn off the disformal deformation, and set all these alphas to be constant. Then you get dRGT. The next to minimal example is the generalized massive gravity. And this was first proposed in 2014, well before us. And this was actually the motivation for us to go look for this general class of theories. And this example can be obtained when you turn off the non-minimal coupling and the disformal transformation. But instead of mass parameters, have mass functions given in this way. And since this is a really big theory class, it becomes really difficult to say definite things about it when it's this general. So I will be simplifying things by making some selections so that I can make more and more precise statements. So the first simplification I will do, I will be focusing only on generalized massive gravity from now on. So let me rewrite the action for generalized massive gravity. To recap, you have for the kinetic term, the canonical Einstein-Hilbert kinetic term, or Einstein-Hilbert action. And you have the dRGT mass terms, but now the mass parameters are now promoted to be functions of the new invariant X. Then we can look for cosmology here and see how or whether this resolves the issues associated with the strong coupling. So let's look for cosmological solutions. And if we impose homogeneity and isotropy of the background, there are two conditions you can have. First of all, one condition is to have the symmetries of F to match the symmetries of G so that this contraction does not introduce any leaking of any inhomogeneities and so on. You also have an explicit dependence on the new invariant in the action. So X should be uniform, should not depend on coordinates explicitly. And if you impose these two conditions, there's a unique choice of field configuration that gives you a homogeneous and isotropic universe. And that's precisely the same configuration that we had for the dRGT case. And that's an open universe. So with this configuration, you again get F mu as a Minkowski in open chart. But also the norm of the fields, or the new invariant X, is actually just a function of time only. So that's the setup. And we can go and look for the background dynamics. And the background equations are listed here. So L and J, the contributions from the mass term, are defined exactly the same way as in dRGT. And in fact, the first three equations are the same as in dRGT. The difference arises from the last equation, which was the Stückelberg equation. And if you remember in dRGT, J was forced to be 0. But now, because of this variation of the mass parameters, which are now functions, so dxL is defined here. So these contain the derivatives of these functions with respect to their arguments. These variation in the parameters actually source a non-zero J via this equation. And this is how you resolve the strong coupling problem. Okay, but you can be more precise than that. You can go ahead and do a proper perturbative stability analysis, which we have done. I'm not going to show you all the results, but we have some closed form equations for stability. I'm just going to show you a cross section of the parameter space. For that, I'm going to make more choices. So I will completely turn off the parameters alpha 0 and alpha 1. I will fix alpha 3 and alpha 4 to be constant. So it's almost like dRGT, except alpha 2 will now still be a function. And its functional dependence on the new invariant is linear. It's taken to be linear. So this is one example. Okay? And this is the example I'm going to take, carry over to the end of the talk. And here, this Q parameter is basically the thing that measures how far away from dRGT you are. So if Q is very, very small, you're closer to dRGT where all coefficients are constant. If Q is sizable, then the departure from dRGT is bigger as well. And depending on the sign of Q, you can have different stability behaviors. So I'm just showing you alpha-3, alpha-4 space here. The green regions are where all of the stability conditions are satisfied. By all stability conditions, I mean stability under having no ghost instabilities, no gradient instabilities, or no tachyonic instabilities for scalar, vector, and tensor nodes. So all of them really. And blue region in both of these plots is where at least one of those conditions are violated. So you want to be in the green region. But also, if you want to use massive gravity in order to explain the late time acceleration, then yeah, that's the part where which becomes a bit more difficult. You want a cosmological constant that is positive. So that matches the sign of what we observe. And that can only be achieved in this shaded region here. Okay, so you want to be in the overlap of the shaded region and the green region, and that's shown in this yellow part. So you want to be in the yellow part if you want to use this as a dark energy model. In both of these plots, there are some regions which actually allow you to do that. And I'm going to, again, fix a point. So I'm going to make even more choices, and I'll turn off alpha-3. I'll fix alpha-4 to 0.8 and just choose Q to be positive. So I will be on this point. So at least this ensures that whatever I do, unless I do something unless I go to some special points, I will be making sure that all the stability conditions are satisfied. Okay. So from here, now we can look at what the example actually predicts. First of all, you find that the mass term actually behaves like a fluid with an equation of state that is less than -1. So this is given here. Let me try to unwrap this plot a bit. So as you go from purple to red, you're decreasing this Q parameter. And Q parameter, if you wish, was kind of measuring how far away from dRGT you were. So as you're going up in this plot, you're getting closer to dRGT. Or lambda CDM, because dRGT and lambda CDM are indistinguishable at the level of background and also scalar perturbations, in fact. So basically, that's what's happening. As you increase Q, you go further down to more and more negative values of W. There's a special part here. There's some feature here as well. Let me also say a few words about that. There's a point when the W starts to turn around towards -1. And eventually, if you continue this evolution, it will cross -1. And that's where things start to break down. And actually, this corresponds to one of the kinetic terms crossing 0. So there's an instability associated with that point eventually. But that's in the future. Again, this can be relatively well controlled by choosing smaller values of Q. And also this type of quick appearance of this future instability can be associated with the simple example that we chose. So I don't worry too much about it. And as long as it's in the future, I don't mind, because my solution before that is still valid. And for the Hubble rate, with respect to the lambda CDM, you get a 1% change in the Hubble rate as well. And let me also point out that we normalize Hubble rate today to coincide with H0. That's why there's no change at this point. So everything is sorted with respect to this normalization in this case. Okay, so this is the background. As for perturbations, we have a scalar mode now that contributes to gravitational interactions, and its effects can be basically absorbed into a definition of a new gravitational constant, G effective. And G effective differs from the G Newton, the lambda CDM value, at about 10% level. Okay, and you can see that gravity is actually stronger with the addition of this new degree of freedom. Okay. So, and of course now our H is changing, the G effective is changing. Both of these effects also change the way matter perturbations evolve. And as a result, you can have a different history for matter growth. And here I'm showing you matter density contrast normalized to the GR value. And you can see that this is about 1% level change with respect to GR. Okay, so up to now, all of the plots that I've showed you is not very new if you're familiar with dark energy models, right? So you can easily find very similar behavior in scalar tensor theory. Maybe the features will be different. There might be some details that are not the same, but the numbers are not so crazy, right? 1% change is a very typical thing in these dark energy models. The difference here, however, in this context is that now our tensor modes are massive. Okay, and this is the part that actually is different than any scalar tensor theory. And here I'm showing the tensor mode mass, which is in units of Hubble today, and you can see there's like a order 10 Hubble masses. Then you can ask, what does this say about LIGO, like LIGO observations, LIGO Virgo, basically, which constrains the speed of gravitational waves? Well, first of all, we use the Einstein-Hilbert action. So the light cone seen by the tensor modes is the same as GR. So the gradient term and the kinetic term basically have the same coefficient. But we have a mass, and this mass actually leads to a slight modification of the speed of gravitational waves. But these are currently well within the bounds from LIGO. So the tensor mass is basically 10 Hubble for this model. And this is like about 9 orders of magnitudes smaller than the LIGO bound. But interesting thing, so if I go back to the beginning of the talk, I talked about the falsifiability. If the future experiments do not see any difference from lambda CDM at the background or scalar sector, then for this model, this will tell us that to put lower and lower bounds on Q. So we have to decrease Q to be compatible with the data. But on the other hand, lowering Q actually means increasing the mass of the tensor modes here. So there's no complete lambda CDM limit in this theory. In that sense, in this model, at least, is not containing lambda CDM in some limit. And in principle, it could be falsifiable, but you have to really make really good, put real good constraints on the tensor mass as well from other places. But at least in principle, the idea is there. Okay, so now we have an extra degree of freedom. You might start worrying about its effect on local tests of gravity. And of course, this is a massive gravity theory where Vainshtein screening was first introduced in the context of. And this indeed has a Vainshtein screening mechanism. To show that in a recent paper, we looked at nonlinear perturbations. I don't have too much time, so I will try to be a bit quick about this. But we looked at nonlinear scalar perturbations. The interesting thing is the scalar fields, we have 4 of them, and in the scalar sector, there are 2 scalar perturbations associated with this Stuckelberg perturbations. The one that is the spatial perturbation, pi, is analog to the scalar in scalar tensor theories. This is dynamical. It also encodes information about the scalar graviton mode, whereas the temporal Stuckelberg perturbation has no analog in scalar tensor theory. Here in massive gravity, it is non-dynamical. If you're familiar with the massive gravity theories, It's the Boulevard-Desert mode, which is an auxiliary field in this context. And this is where all the difference arises from scalar tensor theory, because it lets you have more like a constraint system, if you wish, as opposed to scalar tensor theory. So even though you have one propagating scalar mode, you also have this additional auxiliary field, which changes the picture, and the types of interactions it introduces are quite different than scalar tensor theory. So what we do, we look for spherically symmetric sources, but we don't do a normal perturbative expansion. Instead, we use the distances as an expansion parameter. So we look at short distances and accordingly choose some orders for perturbations such that the second derivative of a perturbation is of order 1, as well as the density perturbations. And this choice is basically to keep the Poisson's equation consistent. So at leading order, the Poisson's equation should be there in this expansion. But apart from this, you're keeping all the nonlinear interactions. And with this, you can go ahead and calculate the gravitational potentials from the Einstein's equations, and you get these nonlinear terms. And up to here, everything is very similar to Horndeski-like theories. But the difference arises once you integrate out the temporal Stuckelberg field. And the Stuckelberg equation of motion has some unique nonlinear interactions. And let me show the equation as well. So this is the master equation for the pi field, or its first derivative, to be exact. And I didn't bother with writing the explicit form of these potentials, phi and psi, but you can see what they are here. They just depend on the source and this pi. And you can see they're not equal, by the way. So this basically is a 9th order polynomial equation for pi prime. So there are 9 solutions. The one you pick is basically dictated by what your perturbative solution is doing. The linear, in the linear regime, you expect to have this type of behavior from your solution. And then what we've done, we've solved this equation numerically and look for the root of this equation that matches the correct linear behavior. And then we made some analytic estimates as well, which fitted perfectly. And the solution is, again, quite unique to this type of theory. It doesn't appear in Horndeski theories, as far as I know. The correct route that we take is the brown one. And there's a weird behavior in the nonlinear regime. You can see that it's adjacent to this red dashed line. And the red dashed line defines the roots of this denominator. So there's a singular point in here, which luckily none of the solutions intersect. But these types of solutions, at least the physical solution that we were looking for is the one that is adjacent to the singular point. And with this approach, we were able to also get an analytic estimate for that. But at the end of the day, we have a linear behavior and a nonlinear behavior. And by matching the two regimes together, we determine a Vainshtein radius. So although the way this solution appears and manifests itself is quite different than scalar tensor theories, the type of Vainshtein radius you get is very typical. So very like a Galilean-like Vainshtein radius, in fact. And then you can also show that the Vainshtein screening is quite effective in this theory. Just concentrate on the red line here. That's the gamma ppn parameter, which is the ratio of the two potentials. And outside the Vainshtein radius in the linear regime, you have a departure from the GR value at 1. But once you go inside the Vainshtein radius, it quickly goes to 1. So it's GR value as fast as R cube. And the current solar system test bounds on the departure of this gamma from 1 is satisfied at about 0.1 parsec, which is well beyond the solar system scale. So Vainshtein mechanism is effective. And let me finish by saying a few words about the dangerous tensor-scalar-scalar interactions that I mentioned in the previous slides in the beginning, actually. And I argued that this may put some tension on some of the models like cubic Galilean and so on in the scalar tensor theories. Then you might ask, do these appear in massive gravity? In scalar tensor theory, these arise from basically covariantization. Any covariant derivative will bring you a time derivative of the tensor mode, basically. And these types of interactions can arise very easily in scalar tensor theory. But we don't have explicit covariant derivatives of scalar fields here, but we have a form of covariantization of the fierce poly theory in some sense. So I don't know whether this is related. This is work in progress, by the way, I should tell you. But if you look at massive gravity, you can actually find both of these terms. So both of them are there. We are still trying to understand the fundamental reason for these types of terms appearing. Maybe it's a feature of lambda-3 theories, but we don't know. We're still considering this. But these basically depend on the background functions, and depending on the model, they can be large or small in principle. I think it is possible to set this term to 0 on any at any time in the evolution. This might be a bit more difficult, but still, just to get an idea on the sizes of these things, let me go back to my minimal example where I turned off 3 of the parameters and set one of them to be constant and had just small departure from dRGT. And in this case, both of these coefficients are larger than order 1. The second derivative term coefficient is order 1, whereas this one is 10 to the 4, as shown here. But on the other hand, if you look at the sound speeds, those are quite large for the scalar mode. And I mentioned in the beginning that Creminelli et al.'s results relied on the assumption that the sound speed was less than 1. So in that sense, maybe it's not that big of a deal. And it's also not that surprising to have a scalar field that is superluminal in this case, because we were building this model, this minimal model, by trying to explain dark energy, and while trying to be quite close to lambda CDM, but not that close. But lambda CDM is the same thing as the dRGT background. And in dRGT, we know that the scalar mode actually has instantaneous propagation. It has infinite propagation speed. So in this case, in this minimal example, the propagation speed is not infinite because we're not exactly on dRGT, but the condition that we are close to dRGT actually implies that CS has to be large. It's not that large though. It's about 100 today, but that's kind of expected. So I think I can now conclude. I'm sorry if I went a bit over time, maybe 2 minutes. But basically, I told you about a new class of Lorentz invariant theories with 5 degrees of freedom, massive gravity theories. And I just chose one proof of principle model and showed that it's not that difficult to get some nice features from these models. My conclusion was that the massive gravity framework is not fully described by the scalar tensor theory, but there are some common conclusions. Like there's a Vainshtein radius, very similar one. There are these scalar tensor-tensor interactions and so on. So that's basically, I think, where I stop, and I can take questions